Hello everyone, welcome to LICD Lecture 40H. Today we are going to discuss the numericals on practical differentiator circuit. So let us start. Numerical number one. So numerical number one statement is determine the output voltage for the differentiator circuit shown below. If the input is a sine wave of 1 volt peak value and 100 hertz frequency. So let us check this out. So the input is 1 volt peak, that is peak to peak value is 2 volts, and the values of RF, CF, C1 and R1 are given as follows. Okay, so let us see now. So we have been given input sine wave where Vm value is 1 volt peak, F is 100 hertz. So Vin will be Vm sine omega t, that is Vm sine of 2 pi f into t. So the output of the differentiator is given by V out of t is equal to minus Rf into C1 d by dt of V in of t. Okay. So the value of Rf and C1 we substitute over here. So the value of Rf is around 15.915 kilo ohms and C1 is 0.5 microfarad, and that will be constant. So d by dt of 1 because Vm is 1 sine omega t where omega is 2 pi f. Okay, so this number, if you multiply, that will come out to be 0.015915 into 2 pi into 100. So that's the value which is coming from here. And the differentiation of a sine will be a cosine. So here is the cosine value cos of 2 pi into 100 into t. Okay, so if you multiply these two numbers, you will get V out of t is equal to minus 0.9999 cos of 2 pi 100 into t. So almost equal to minus 1 basically. So here is my output. Actually, for the sine wave input, my output will be a cosine wave of peak amplitude 0.9999. Okay, so let's check it out in LT Spice. So I have already built up the circuit. We have applied a sine wave and we are expected to get an output cosine wave. So here is my input and here is my output. Okay, so that's the value which we are getting. Let me expand it. So as you can clearly see, the V out is slightly lesser compared to V in. That's because we are getting 0.99. And here also it's confirming, I believe, it's 990 millivolts. That is around 0.99 volts. Okay, and it's a cosine nature. Yeah, it's actually cosine inverted, like because of the minus sign. So if you come back over here, output is really indeed a cosine wave with a peak amplitude of 0.99. In reality, it is 0.99. Theoretically, we are getting 0.9999. Okay, so the orange color curve is the sine wave and the blue color is the cosine wave. This is the expanded view showing that the amplitude over here is 990 millivolt, that is 0.99 volts amplitude. So these are the input output waveforms for a differentiator with a sine wave input. Now let us move on to the second design. So the second numerical says determine the output voltage for the, actually it's a differentiator, statement is wrong. So determine the output voltage for the differentiator circuit shown below if the input is a triangular wave of 1 volt peak value and 100 hertz frequency. Okay, so we have been given a triangular wave where whose peak value is 1 volt peak to 1 volt peak, and here the frequency is 100. So the time period will be around 1 upon f, that will be 10 milliseconds. So this waveform over here will have rising from -1 to 1 in 5 milliseconds, and it's falling from 1 to -1 in another 5 milliseconds. So the design, the circuit values have been given. Component values RF, CF, R1, C1 is given to you. Okay. So let us analyze this further now. So we have been given an input triangular wave of 1 volt peak and 100 hertz frequency. So let's analyze this a little further. V in input. So we'll divide this into two intervals from 0 to 5 milliseconds and from 5 milliseconds to 10 milliseconds. Okay. So over here, if you see carefully, the frequency is 100 hertz. So time period will be 1 upon 100. That will be around 10 milliseconds. So that is the time period of the input waveform. Now let's divide this triangular wave into two parts. So the first part, the time is from 0 to 5 millisecond. Okay. So from 0 to 5 millisecond, we are considering the rising edge of the triangular wave. Correct? So what is the rising edge of the, what is the slope of this line? The slope of this line will be y2 minus y1 upon x2 minus x1. So what is y2 minus y1? So it is 1 volt divided by, sorry, minus of minus 1 volt divided by x2, which is 5 millisecond and x1 is 0. So you get a number 2 upon 5 millisecond, that will be m will be equal to 400. Okay, and basically it's a straight line but not passing through the origin. So what will be the y-intercept of this? So y-intercept, if we shift this waveform up, automatically you will get a y-intercept of 2 volts. Okay, if you shift this up by around 1 volt up, this will go to 2 volts. So that means the y-intercept is 2 plus 2. So if you arrange it in the terms of y is equal to mx plus c, m we have calculated, it is 400. C is actually, sorry, I have said around plus 2. It's actually minus 2. Okay. So if you shift this actually if you shift this down, you will get a minus 2 y-intercept slope. Okay. I hope that this point is clear. If not, please analyze the waveform, input waveform carefully. So y is actually v in of t, x is t. So here y is input voltage with respect to time, and x axis is t. And the y-intercept slope from 0 to 5 millisecond is around minus 2. Okay, so you can work it out mathematically why the y-intercept slope is minus 2, y-intercept coordinate is minus 2. So v in of t is 400t minus 2 for the period 0 to 5 millisecond. Now similarly, we will analyze from 5 millisecond to 10 millisecond, which will be a falling edge of the triangular wave. So from 5 to 10 millisecond, falling edge of the triangular wave, what will be y2 minus y1? So it's a falling edge, right? So it will be minus 1 divided by 10 millisecond minus 5 millisecond. That's what it is. So let us check it out. Yeah, so it is minus 1 divided by 5 millisecond, that is minus 2 divided by 5 millisecond. So the slope will be minus 400. Similarly, here again we arrange in terms of y is equal to mx plus c. Now this time the y-intercept will be plus 2. So you can work it out why the y-intercept will be plus 2. I leave up to you. So from the interval 5 millisecond to 10 millisecond, y is the y-intercept as plus 2. So you all can check it out. So if you substitute it over here, V in of t is equal to minus 400t plus 2. Now, the output of the differentiator is given by the equation V out of t is equal to minus Rf into C1 dV in by dt. So for the rising edge of the triangular wave, V in of t is given by 400t minus 2. So if you open it up, you will get d by dt of 400t will be 400, d by dt of a constant value will be 0. So it will be, you have to just multiply these three numbers, 15.915 kilo ohms into zero point 0.1 into 10 is to minus 6 into 400. If you work out in a calculator, this number will be minus 0.636. That's the number which you are getting. Similarly, for a rising edge of the triangular wave, here it will be minus 400t plus 2. So the result will be remaining the same. Only thing is the sign of the output will be different. So V out of t will be plus 0.363 volts. So output will be a square wave of amplitude plus or minus 0.636 volts. Okay, for the entire duration of the rising edge and the falling edge of the triangular wave, it will be a constant either at plus 0.36 or minus 6.36. Okay, 0.636 actually. Now let's test it out in LT Spice and check. So I'll go to LT Spice and I'll close this. This is not required. Next, practical differentiator with a triangular wave input. This is what we want. And let's simulate this. So actually the values have to be put in very, very carefully over here. So let me open that PDF. Okay. So the values which you are about to put in LT Spice are as follows. Let me just reduce this. Okay. So this will be 1.5915. Actually, we put it exactly as that. Those were given over here. This is also 1.15.915 kilo ohms. Okay, so all the values are done. Now we check out the output over here. So whether it is a square wave or no. So we'll go to simulate, we'll click on run, we'll plot the input triangular wave going from -1 to 1 and subsequently repeating, and here is my output. Okay, don't worry about the charging discharging, that takes place because of the two capacitors. Let's concentrate on the magnitude. So over here, if you check out, the magnitude will be 0. 636 millivolt, that is 0.636, which is exactly what we got. And here it is minus 636. Okay, so that's exactly precisely what we are getting over here, and that is what we predicted. That let us go back to this. So for the rising edge for of the triangular wave, my output will be at minus uh, 0.636. So here it is minus 0.3636. And for the actually second one is for the falling edge. So for the falling edge, the output is at plus 0.636 volts. Okay, so that's the value which we are getting. Now I'm just taking this. I've taken the print screen of this and attached it on the OneNote PDF. As you can see, they both are the same. So from this we can see clearly that the output is a square wave, and the input, if input is a triangular wave for a practical differentiator circuit, and the values are also quite matching. It's around 0.636 volts, and negative value, the negative peak of the square wave is minus 0.636. So these are my input output waveforms for a differentiator when a triangular wave input is applied. So that's it for this lecture. So we have completed the two numericals for a practical differentiator circuit. So next time we'll see the comparison between the Opamp integrator and the Opamp differentiator circuit. So until then, have a good day and thank you.